the curves that we looked at were completely above the x-axis. But not all functions are going to be above the x-axis. So what happens when we go below? What's going to happen to the y values when I pick my heights? They're going to be negative. So when I go below the x-axis, I'm going to get a negative contribution. And when I'm above it, I get positive contributions. As n goes to infinity, we're not going to see all the rectangles anymore. So we're going to have these areas on this second graph that also are going to give us positive contributions when we're above the x-axis, negative when we're below it. What this tells me then is we're not calculating just the area of the curve. We're calculating net area. It's going to have some positive, some negative contributions. Okay, so what all of this gets us to is called a definite integral. Now, we were doing integrals when we did our antiderivatives, right? So we recognize this symbol already. That's the integral symbol, but now I have lower and upper limits on it. Because we need to know where are we finding the area, from what x value to what x value. So I have my lower limit is a, my upper limit is b. This s thing here, it's like a squished but elongated s, and they use that symbol because it's a summation of all the rectangles, right? So it stands for sum, but we just call it the integral symbol. This right here, the function, is called the integrand. And then we know the dx is just telling us with respect to what variable, but it's kind of the same thing as my delta x over here. And so what happens when we take the limit as n goes to infinity of the Riemann sum, we get a definite integral. And it gives us the exact net area. Okay, there's a lot of properties of definite integrals that are also properties of regular integrals, but these are specific to the limits. The first one is that if I take the integral from the lower limit of a to b, if I switch the limits, I will get the exact opposite net area. So going from left to right, and then switching and going from right to left will give me a negative answer. If I integrate from a to a, it gets me nowhere, right? I'm trying to find the area under a line. There's no area under a vertical line. So we get 0. If I integrate over a constant, I will get the constant times the upper limit minus the lower limit. Well, that was the very first thing we did, right? We had a constant speed, and then we multiplied over by t equals 4 hours. That was my upper limit was 4 minus my lower of 0, right? So when we integrate over a constant, we're just doing a rectangle. We're finding the area of a rectangle. If I integrate over the sum of two functions, we did this when we just did antiderivatives. It just means I can split it into two different definite integrals. Okay. If we integrate over a constant times a function, we can just put the constant out front of the integral. Right? Just like when we did derivatives, if we had a constant times some function of x, we keep the constant there. We do the same thing when we're going backwards. If I'm integrating over subtraction, I can split it into two different integrals, one subtracted from the other. I can't think of a reason why I'd want to, but I also could change this one to plus the integral over g of x if I switch the limits, right? I've never found a good reason to do that, but I could. And then here for number 7, what we're looking at is if I'm integrating over some curve, I'm trying to find the area. I can break it up into the area between A and C plus the area going from C to B gives me the total area from A to B. Okay, so let's use these properties to find some definite integrals. If I know the integral from 0 to 10 of f of x is 17, and I also know that the integral from 0 to 8 of f of x is 12, then I can find the integral from 8 to 10. That's going to use that last property, because here we're breaking it up as if our c is 8. So we could say that the integral from 0 to 8 of our function plus the integral from 8 to 10 of our function equals the integral going from 0 to 10, the whole area. And we know from 0 to 10, it's 17. We know from 0 to 8, it's 12. So I have an equation here. So my integral from 8 to 10 would be what? It's going to be 5, right? 17 minus 10 or minus 12 is 5. All right, what if I asked you to find the integral from 0 to 10 of 2 times my function minus 5? Well, that constant multiple property tells me that this would be 2 times the integral from 0 to 10 of f of x, and then minus 5, we can write it as a separate integral from 0 to 10. And there was a property for that, too. That's integrating over a constant. So for the first one, we're just going to get 2 times the integral from 0 to 10. So that's going to be 2 times 17 minus 5. That's the property for a constant that gave us the constant times the upper limit minus the lower limit. So I get 34 minus 50 is negative 16. So that negative 16, what does that tell you about this function if I were to graph it? Most of it would be below the x-axis.